So again, talking about feature learning, specifically with matrix factorization and neural networks. And can everybody hear me okay in the back? We good? All right, cool. So I'm a data scientist, and this Venn diagram is one of the first things that came out to explain kind of what is a data scientist, what's data science. And I jokingly with my coworkers kind of say that I kind of thrive in the danger zone only because I have a background in programming and I come from I have a computer science degree. I have less of the knowledge on the math and stats, and I do have significant substantive expertise, and really a lot of that, the blue circle is really communication as well. How can you communicate your results to people? And I find that I'm very good at that and the programming part. I don't have a math degree, so I'm not as strong in the math and stats. Even though it says it's a danger zone, I think there's a place for people like me, and they still called me a data scientist, so that's hope for some of you who don't have a PhD in math. So, I work for a company called Modernizing Medicine. We're an electronic health record company. We have about 40% of the country's private practice dermatologists on our system, and we are hiring. So if anybody's a mobile engineer, iOS, web engineer, Java, or a data engineer, we need those people, so talk to me after too. And if you want to contact me, that's pretty much RIKTR. Anywhere on the internet you can find me like that.
And on Slack, you guys can find me on Slack.
Yes, I'm on the Slack too. So this is kind of a bad habit from academia, but here's an agenda slide. So this is what we're going to talk about. So I won't spend too much time here because we're going to... Yeah, exactly. We're getting super meta about this stuff. So we're talking about feature learning, and then feature learning, and then some code. So let's dive into it. All right, so, well, first of all, what is feature learning? It may be something that a lot of people haven't thought of as a separate field within machine learning, because a lot of algorithms will kind of do this inherently. So, basic concept of feature learning is extracting features from raw data. So a lot of the times it'll happen when you're doing some sort of image detection model. Anytime you need to do anything in machine learning, you need to create features which are your input data to your machine learning model, so that way the model or algorithm can actually learn something to predict. So feature learning specifically is actually using these machine learning algorithms to intelligently create those features rather than making it by hand. So some other names that you can find, it called in literature throughout is feature embedding, feature extraction, representation learning. I've always called it feature embedding myself, but preparing for this talk, I found the Wikipedia page on feature learning, and I'm like, all right, so I mean, Wikipedia is the authority, right? And I think it sounds cooler anyway, so feature learning it is. And so again, so that's what, from a high level, feature learning is. We're going to go to some examples of how this actually happens in practice, but why do we need to do feature learning in the first place? And so that's where this graph comes in. This is basically very highly simplified workflow of a machine learning predictive analytics model building workflow. You start with some data, right? You start with some data and you start with a problem. You don't just start with data because you need somewhere where you're going to go with the data. You start with your data, you start with a problem, and you have to clean that data because all the data sets aren't going to be nice, pretty, clean data set that you get from UCI to build a machine learning model on. So that purple part is most of the work for anybody who's really done this in a real setting with real data that's not really a toy data set or academic data set or even a Kaggle data set. Those are very canned and predefined for you. That's where most of this work is, and it's not all feature learning here. It's feature engineering is part of it. It's cleaning data, it's joining data sets together, it's filtering out bad stuff, data quality, all that stuff. And then after you get past that, you can get to the fun stuff. I mean, I think the feature engineering is the fun part, but I think I'm kind of weird, I guess. But then you get to the fun part where you get to train a machine learning model, you get to test it, you get to improve it, you get to deploy it, and all that good stuff. But so we're going to talk about the purple part, but we're going to bring some of the modeling into it, so it's going to be fun too. It's not just going to be a bunch of data cleaning. So here's a good quote that I found on the internet from Andrew Ng, and again, why do we need feature learning? Is because feature engineering is hard. Manual feature engineering is difficult. To go and find a data set that has like 300 columns in it, or that has 5 different tables, and you're getting it from different sources. You need to figure out how to combine that data together, and then you need to figure out, okay, what features is the machine learning model going to actually be able to learn from? And as he says here, most of machine learning is just applied feature engineering, because these days all the algorithms are available for you. And that's why I find that I'm not really lacking a lot as far as kind of applied machine learning, that I don't have the math background, because I can just go, import scikit-learn or, library keras or caret, and then I have all this, wealth of machine learning knowledge ready for my disposal and easy to use APIs. So the real challenge with a lot of business problems is creating those features and creating those so the machine can actually learn them really well. So some kind of quintessential example application, this is kind of the shiny stuff that Thomas mentioned, that feature learning does really well for are things like computer vision, image detection, and text, because of the fact that these are very high-dimensional kind of raw inputs. You think about an image, and it's basically just a set of pixels. Every single pixel in that image can be a feature to your data set. So when you train a neural network, as we'll see later on in the talk, when you train a neural network on images like that, it internally creates this latent feature space, which is actually feature learning. Most of the time, you're actually trying to predict something, so you kind of miss the feature learning because you're seeing that, okay, hot dog, not hot dog, it works. So, but you don't get the middle part where the features are actually being learned, and that's what we're going to talk about today. And that's really what it's about. Text mining is the same way. There's lots of words in every language, and you can use those to learn some features. Another one, just shameless plug for myself. This is a screenshot of our application at Modernizing Medicine, and I actually am working on my PhD as well. I don't think I mentioned that at FAU. And I'm using the data from Modernizing Medicine to do some predictive analytics, see if we can help people in medicine. So the project that I worked on was around melanoma. Basically, once a patient gets diagnosed with melanoma, there's a chance that that melanoma has spread to a lymph node. So it could be that it's just localized to the skin. If you excise the tumor, patient's good to go, and then there's no more melanoma. But if the melanoma has spread, the first place it's going to go is to the nearest lymph node. So I was building a model to try to predict the risk of that lymph node metastasis, which is what that's called. And there's a biopsy that can be done on the lymph node to do that, but basically this model would be to help guide the physician on determining if that lymph node biopsy is even necessary. So you can read the paper, talk to me more if you want some more details, but the bottom line of this was like a 6-month project. I had to take the data, raw data inputted by the doctors at the point of care, do a whole bunch of ETL, joining data, cleaning data, figuring out the edges of the application, removing messy data, all that stuff. And then I had to do the feature engineering, and then I got to do the machine learning. So a 6-month project, probably only 2 of that was spent in machine learning.
Does anybody not know what ETL is?
Oh, true.
So,
Yeah, no, thank you.
Quick description.
Yeah, absolutely. So ETL is just a jargon for data cleaning, essentially. It stands for extract, transform, and load. So you basically extract data out of a source system, so something like this, where it's in a traditional relational database system. Those are architected for reads and writes, fast reads and writes, multiple people doing it at the same time. What ETL does is it takes data out of that, cleans it, and formats it in a way that's more usable for analysis. So when you hear terms like data warehouse, that's what ETL is doing, is taking that data from the input systems, doing some ETL into a data warehouse or curated data set, and then from there you can now start to do your feature engineering, and then subsequently your machine learning.
Thanks, sorry.
Yeah, no, absolutely, thanks.
Aaron, can you briefly describe the types of data that you were combining to solve this problem, or to try to learn features to solve the problem?
Yeah, sure. And so everything here is captured by basically outpatient private practice dermatologists. So this is when you go to the dermatologist and the medical assistant comes and talks to you and says, hey, why are you here? All that data is captured. Those are why the patient is presenting. Let's say I'm coming with a suspicious skin lesion. We're going to have all the data and all the metadata around that. And what's unique about our system is that it's hard to see it on the screen, but everything is touch-based. So there's no free text, there's no dictation. Everything is structured inputs that's actually created by doctors on our staff. So from there, we get all the patient's history, we get their vitals, we get all of the billing information, all the charges, the diagnosis codes, the procedures that were performed on the patient, all their prescriptions, past medical history, allergies, anything that a doctor would need to treat you at the point of care. That's what's all collected in this electronic health record system. And so that's the kind of data we're dealing with.
Are they all text-based?
Well, I mean, it's text, but it's structured. So it's like, for instance, rather than typing in, I counseled the patient for psoriasis, we actually have a specific button that they click for counseling once they've clicked psoriasis. So it's all structured. It's not like we have to do really NLP on it, but it is kind of textual in that manner. So because of that, because there's a bunch of structured inputs, there's literally hundreds and thousands of raw features in the data because there are so many diseases, there's so many specific data points that you can collect on all those. But from reading literature, from working with multiple dermatologists, and because of just the sheer vastness of the data, we landed on about 30 manually engineered features that, again, that took 6 months to, 4 months to pull those through, to kind of clean it, make sure that, if one feature was actually recorded in multiple places of the application, you needed to reconcile, make sure those are the same. You need to, normalize data and all that stuff. So we ended up with 30 features, and again, the particular problem I was trying to solve, the sentinel lymph node biopsy, I only had about 5,000 labeled instances of that for that particular variable. But I have, millions and millions of patient visits, but only a certain amount of people have melanoma, and then only a certain amount of doctors opted to record this particular variable that I wanted to record, because it's all optional. It's a real-world system. So I had to use 5,000 labeled instances, 30 engineered features, when I could have somehow used 2+ million unlabeled instances, which means instances where I don't know the actual outcome. I don't know if the patient had a sentinel lymph node positive or negative. And then I had to use these manually curated features. And the paper found that, kind of depending how you count, sometimes the machine learning model will help in a certain scenario, but a lot of the times it was just kind of like the basic biology of the problem. The machine learning models couldn't really do much better. And so that's where kind of I'm trying to go towards with feature learning, is that rather than me and doctors trying to upfront figure out which features we think the model is going to pick up on, why don't we just give it everything, let it learn some latent feature space, see how that does, and then kind of back into that and try to explain that feature space afterwards. So a couple considerations for feature learning, and then we'll dive into how you actually do it. It does work best with some of this high-dimensional, quote-unquote, raw data. So when you have basically lots of data, because what feature learning does is it takes your input space and it condenses it down into a much richer feature space. So obviously, if you only have 10 features to start off with, there's only so much condensing you can do and so much you can do as far as learning some new features. So it is a form of dimensionality reduction, which means reducing the amount of features that go into your machine learning model, which obviously is a nice thing to have for computational purposes and for time. One thing to consider, though, and perhaps why adoption is limited in certain areas like medicine, is that model interpretability is limited. So if you have a model, let's say, trying to predict a housing price, you can have the zip code, you can have the size of the house, you can have maybe 10 features that are very easily understood by humans. And then you can build like a regression model or a decision tree where a human can go and follow the path. They can say, okay, well, if it has more than 1,000 square feet, let's go down this point. It's got to be over X amount of money. Or if it has over 3 bedrooms, we know that it has to be above this particular threshold. But with feature learning, it's the machine learning the underlying data, and it can be difficult to interpret what the machine is actually kind of doing under the hood. So I'm not going to talk about that too much, but this is an active area of research that is really, really important, especially when you're talking about certain applications where interpretability is really important. So before I go into how to do feature learning, any more questions on just like what feature learning is, the basic concepts? I think things will get kind of easier to understand as we kind of go through some examples, but any high-level questions at this point? Cool. It's a nice break for beer too. All right, so 2 forms of feature learning, which goes along just with any other machine learning, is there's unsupervised learning and there's supervised learning. So what supervised learning is, I'll start off with, it's a little bit more straightforward, is if you have a very specific problem and you know what you want to predict, you're doing supervised learning. So in my particular case, where I have a data set of melanoma patients and I'm trying to predict whether or not these patients have sentinel lymph node metastasis, those 5,000 instances that I had all had labels, meaning I knew for sure whether or not that melanoma had metastasized. And so that's a supervised learning scenario where all of your data has class labels. Unsupervised is where you're actually just trying to learn patterns and representations from the data without a specific problem in mind. So in my example, I had 5,000 instances with a label, but I had over 2 million that I didn't know if they had a sentinel lymph node biopsy. I didn't know what the result was. But you can still train some sort of model on that data set where it can learn patterns just within that data set alone without actually trying to use it for a specific problem. And that's really interesting and really useful for if you're trying to condense down some sort of input space and then trying to predict, let's say, multiple problems. Or you're just trying to understand the relationship between your data. You're trying to understand what's going on. Yep.
You can use it as pre-training.
Sorry?
You can use
absolutely.
As pre-training.
Yes, and we're going to...
For your label set.
Exactly, and so you can. That's almost like a bootstrapping where you can start it off with your unlabeled data and then learn some sort of feature representation, can maybe start it off that way, and then you take that representation, switch that over to now your labeled set, and then kind of just fine-tune it afterwards. So definitely.
And you could avoid a bunch of local minima with that.
Yeah, absolutely. And we're going to go through a little bit of examples there. And then transfer learning is another interesting topic that I'll get to and kind of explain a little bit more. But what we're going to go through today specifically is just really high level on matrix factorization, what it is, not really much on the maths, but just like what it is, how is it used, some considerations. And then we are going to talk about neural networks because those are the shiny fun things to talk about. But the examples I'm going to show with the code is going to be with some actual other medical data, not from my company, but so something that's not images or sound or text. So should be hopefully eye-opening, and that's really what the goal of this presentation is from my perspective, is to really show how we can be creative with machine learning. How can we apply some of these techniques that are really useful for these really important domains such as images and text, but bring it back down to like our real-world bottom line. Like if we're trying to predict customer churn, if we're trying to figure out if a customer's going to stay with us, or anything else in your business. The goal of this is really like how can we start to use some of these methods in the quote-unquote real world. So a quick aside, talking about machine learning and then talking about some of these other models, I have a lot of respect for Francois Cholet. He's the guy who wrote keras, which is a neural network API framework that abstracts a lot of the math away from things like TensorFlow or Theano. And we're going to use keras actually in this presentation. But I thought this tweet was great from him because it's basically like you don't need deep learning for everything. You don't need to do this. For 95% of your problems, most of the time a regression model is going to work just fine. It's going to be much better than humans just making guesses at whatever the data thinks, whatever they think the data says. So we are going to do neural networks because it is an awesome and it's really fun thing to do. But I do want to say that I was very skeptical about neural networks. I know when I first came to this meetup, I'm like, oh man, it's all deep learning. Like, where's all the other stuff? But I've recently kind of cut the bug a little bit. So it's really cool. And you'll see later that there's some really, really interesting creative things you can do with neural networks. But I can't emphasize enough that start with a regression model first or a decision tree and see what happens. So matrix factorization. Again, I don't have a really in-depth background in linear algebra or statistics for that matter. So don't take my word for anything. I'm again going to go high level. This is just from a application perspective. Like what can I use? What can I do? How can I understand them enough to be dangerous with these things? So matrix factorization might sound like a scary term for somebody who's not from math, but it's actually exactly what it sounds like. So when you have factors, you can multiply them together and get something. So that's what matrix factorization does, is you take a matrix, you're splitting it up into other matrices that can reconstruct the original one. So what's really awesome about this, and I do want to learn about the math because it's just like really, this is just straight math, and it like has real effects on the real world and stuff that we can do with data, which is fascinating and it's awesome. And there's like all these people for years who have been coming up with, doing all these theories in academia, and now we're seeing like real big effects in the real world. So it's awesome. And they're super efficient because it's just matrix multiplication. So a couple commonly used ones and terms you'll see that, again, are kind of scary to me, but you'll see eigendecomposition. So if you hear the terms eigenvalues, eigenvectors, that's kind of where that comes in. And singular value decomposition are two big ones that are used. And I'm mentioning them because the next thing that we talk about, principal components analysis, uses both of these. So first one, just talk real quick about singular value decomposition. This is the only formula you're going to see today, and I can explain it because there's only 3 things on the formula. So what you really mostly want to be concerned about is that what SVD does is, again, it splits a matrix into these three other matrices. And the key here is that middle one, sigma, is what's called singular values. It's a diagonal matrix. And from there is basically, those are your singular values that you used to project your input data onto this new space. So what SVD does is it takes whatever training data you have. So let's say whatever you're wanting this model to learn from, you give it that data. Again, this is an unsupervised example, so there's no class labels here. It's just taking the data as is. You give it a matrix, which is your data. It'll, do whatever stuff. You just do, scipy.svd or whatever it is. So scikit-learn, and it'll split it up. And then what it gives you back is a trained model that has these singular values. So now, once you see new data, you basically just project this new data through those singular values, and then you get some sort of transformed data set matrix that's actually smaller in size, less dimensionality. So that's as far as I can go. Don't ask me anything else on that. Another cool one, and this is really interesting and really intuitive, I really highly recommend that you click this link here at the bottom on Stack Exchange. And principal components analysis is, again, it's a method that uses matrix factorization. And this is something that's very, very frequently used in machine learning spaces. And a lot of times it's kind of the first thing you'll try. If you have a high-dimensional problem, a regression model is going to take a long time to learn from thousands and thousands of input features. So throw it through PCA, you can split it down into maybe 30 features, and you can find that it's actually really useful. So the main concept with PCA is that you're trying to extract components, so a principal component. You're trying to pull out basically new features that can maximize the variance of the input features. So one property it has that every time you pull out one of these principal components, it's orthogonal to the previous one. So the way that goes is that the first component captures as much variance as it possibly can in the data. The second component now captures the second most variance it could possibly capture, and then third, fourth, fifth, so on. And what that does is when you're capturing variance, you're actually capturing differences between your data points. So if you're trying to predict, let's say 2 different class labels, those differences in your data points probably are going to be the differences that lead to whatever class you're trying to predict. So again, this is an unsupervised method. It learns it just from the data, but the intuition is that there should be some sort of difference in the distribution of an instance that has a positive class label versus an instance that has a negative class label. And this is a fun little graph where when you read the Stack Exchange thing, this made it click for me. I've always known what PCA was. I've always roughly known how it worked, but this really made it click. So again, I encourage you to read that. We're going to breeze through a lot of this stuff, but this is a good one. So 2 ways to get it, and that's why I introduced these 2 different matrix factorization methods. It's really cool because you can actually mathematically prove that these 2 methods are the same. One is you can do an eigenvalue decomposition of basically a correlation matrix, which is a matrix of correlation between your features. That's a square matrix. Or you can just do a singular value decomposition on your original data matrix. Couple, rules of thumb for doing this is that a correlation matrix is going to be a much smaller matrix most of the time than your input space, because you're going to get a square matrix that's basically just m by n, I think, right? M is the features, or n, I don't remember. But either way works, and if you use scikit-learn, you don't really care which one it does. It just does it really fast. So there's a bunch of links down here if you want to read more on it. So this is another shout out to one of my friends and colleagues, Eric Golinko. He's actually working on his PhD research and creating his own feature learning, feature embedding method. So he actually has a math background, so he could talk your head off about this. I'm just going to show you a pretty graph and show you that the left side here, let's see, what is the left side? Left side is his method. Basically, he's creating a feature learning and projecting it onto a supervised problem. So basically, he has a data set that has 3 class labels. In an unsupervised manner, you can say, okay, learn some sort of feature representation from the data without knowing anything about the labels. And then you can graph that on a 2-dimensional plane, and then we color each dot based on which class it actually belongs to. And obviously, the better separation you have between clusters, the better your algorithm is doing about learning the inherent features and actually split that apart. So the right side is PCA, and the left side is GEL, his method, and you can see that it actually does separate the classes better than PCA does. So really cool. If you want to read his paper, hit him up on Twitter. I think it's out online as well. So some really, really cool stuff. Okay, so that's the matrix factorization part. Now here's the shiny neural networks. And it's really cool because I think actually neural networks are a great way to teach feature learning because you can actually see it happening. So for anybody that's not familiar with neural networks, I know a lot of people here talk to it and are way better experts than me on it. But the basic concept here is, at the end of the day, it's just a big group of linear functions, regression functions, right? So each one of these dots is called a neuron, loosely labeled after the human brain, very loosely. But what you do is you basically, it's basically a regression model in each one of these dots. So you're taking your input data, let's say that's the first layer here. Let's say my data set has 784 features, and this is from the MNIST data. Yep, so the MNIST data, if you're not familiar, is a data set that's basically one of the go-to benchmarks for image detection in computer vision. It's just a series of handwritten digits. And so all of them obviously have a label of what the digit actually is, but a lot of people benchmark their machine learning algorithms to see how well can a machine learning model learn what those handwritten digits actually are in real life. So they're 16 by 16, something like that, whatever the square root of 784 is. Yeah, 32 by 32, there you go. So 32 by 32 images, so obviously you have 784 pixels in those images, and that now means one pixel corresponds to each one of those dots, which is your input layer. Each one of those dots is an input neuron. So what you do is you have multiple layers of other neurons that lead up to an output layer. So your output layer now has one neuron for every class that you're trying to predict. So in this case, it's digits from 0 to 9, so we're going to have 10 neurons. So whichever neuron has the highest output value in this particular case is where we're going to say that the model is saying that the image is. So in this particular case, 7 fired the highest, so the model thinks that whatever your 784 input pixels were predicted a 7. And so that's the input layer and the output layer. What you have with a neural network is, at least, you don't have to have one, but you have hidden layers in between. And so what that does is when you combine all of these linear functions, each one of these dots, let's say on that second layer, that bottom one is actually taking an input from every single neuron in the previous layer. That's creating its own function, spitting out an activation, which now goes to the next layer, and then if you have more layers, it kind of goes so on and so forth. So what that does is that's the quintessential deep learning, and that's why it's called deep, because there's multiple layers in the network. But what that does is now creates these nonlinear correlate combinations. The model is learning some nonlinear combinations between the input data because you're feeding it through these multiple layers of networks. And so why this relates to feature learning is that this final output layer now has some sort of set of weights. So when you think about a regression model, there's biases and weights, and so you have certain weights for each one of your inputs, and those now get trained onto those neurons. And when you project new data through, the features that come out of that last layer are now your learned, quote-unquote, latent feature space. They're not something that's readily interpretable by a human, but it's something that the machine is learning because it's trying to get to its final problem, which is predicting the images. Anybody have any high-level questions on that? I know a lot of people here already know what this is, so I don't want to spend too much time. Yep?
Yeah, I guess I'm just curious, like, on the hidden layers, like, is there any type of, like, mathematical representation for, like, how many neurons end up in each layer of the hidden layers?
I wish there was. So it's like design. A lot of it is hit or miss. There's some guidelines, and based on what other people have done, it's kind of specific to your problem, a little bit specific to your data set. But a lot of times it's just try some and see what happens. There are some guidelines that people have there for, like, if you're trying to make your model, really, depending on the problem that you have. But I don't know of anything where there's like a mathematical way to determine what your network architecture should look like. If there is, that would be amazing, and I hope you're saying something. You can kind of bring some more information.
Everything you said is obviously right, but we're going to do one. I know we have another talk coming up, but I'll probably do the following one, and we'll cover, using Bayesian optimization for hyperparameter searching. There is a pragmatic way to go about searching for the right hyperparameters, but there's a lot of caveats. Like, you're not Google, you don't have 1,000 GPUs. So it's very hard to set off the experiments that you need to do this. And Bayesian optimization does a good job of balancing exploitation of what you already know So we'll cover that at some point. That's a little bit off topic, but there is a way to methodically search the hyperparameter space.
Yeah, and that's a big problem because when you look at something like this, you now have one regression model essentially on each one of those dots. So a typical logistic regression or linear regression, you only have to train one dot, and that might take a couple minutes if you have really high dimensional data. But now you're training all of these neurons, and that takes a long, long time, as we'll see kind of in some of the toy examples. If you want to learn more about neural networks, check out this YouTube link. This is from somebody who did a lot of Khan Academy videos. You might recognize the voice. But this is probably hands down the best introduction to neural networks I've ever seen. It's like a 3 or 4 part video series. They're like 10, 15 minutes each. But again, it's one of those things where it makes it click for you. The animations are awesome, and he does a really great job of balancing.
3 blue, 1 brown.
Yes,
guys.
3 blue, 1 brown.
Those guys.
Yeah.
Definitely look
Yeah,
at
it's fantastic. Like you'll probably learn way more from him than me, so it's really good. So here's just a little bit of some background on the types of neural networks that we have. So what I just showed you before, where every single layer was every single neuron was connected to every neuron from the previous layer, that's what's called a multi-layer perceptron, or a feed-forward, a fully connected network. There's all kinds of different neural networks, and this is where all the fun research is, and this is where all the cutting-edge stuff is coming out. I won't go through all of these, but what we're going to talk about today is you can see there's supervised and unsupervised methods. We're going to talk about specifically autoencoders, and we're going to talk about multi-layer perceptrons, like what I just showed you before. If you want to dive into some of this other stuff, it's really awesome, and it moves so fast. Like I'm learning a lot of it myself too. So autoencoders. So this is a good introduction to neural networks, and if you go on, actually I link it here. Keras has a blog post about just kind of getting your feet wet with actually doing this in code with Keras. And so what autoencoder essentially is, it's a normal neural network, just like I showed you on a couple slides ago. But rather than predicting a specific class that it's trying to figure out a specific problem, what it does is basically just tries to reconstruct your input. So your input layer actually looks exactly the same as your output layer. But what you get there is your model is now going to learn all these weights in your hidden layer that's trying to reconstruct now your output. So you're basically creating a supervised problem. It's not fully unsupervised. It's more of a self-supervised method because you are predicting something. It's not like matrix factorization where it's kind of just working on itself. And that's where a lot of the creativity actually comes in with neural networks, as we'll see. But what's interesting with the autoencoders is that you actually don't even care really how well it does with your last layer. I mean, you want it to work a little bit, but you really don't care about predicting your last layer because why do you need to reconstruct your data when you already have your data? But what you really care about is those input, those green nodes, the latent feature space, your hidden layer, because what that does is now creating some way for you to project the original data back through. Now you have less features because you have less neurons in your hidden layer than you do in your input layer. And this is something that's really, really useful, again, when you do have lots and lots of unlabeled data, and then you have a small amount of labeled data. Do you have a question?
You need to care about the last layer because you cannot steer manually what the representation space is doing. So the only way you can steer it is seeing the output. That's why on autoencoders it's so important, the loss function.
Oh, yes, yeah, absolutely. Sorry, and I think I might have misspoke there. Yeah, you definitely want to make sure that it's minimizing the loss function. It's working really well.
As a matter of fact, it's the only way you can correlate that you're doing a good job on the hidden space.
Yeah, absolutely.
That's what he was trying to say.
Yeah, and it's so sorry if that didn't come out right. But what I meant is that at the end of the day, once you have a good loss and you're confident that your model is actually predicting this well, you don't use your final layer. What you're using is the hidden layer.
Right. The task is to learn a representation, is I think what you're trying to say.
Yeah.
So what you're interested in, even though for training purposes, of course we need to have, which in fact is just a distance function to tell us how bad from the original we are. You don't care about that. Once it's done training, what you care about is the representation learned by the hidden layer. As a matter of fact, if any of you didn't know this, before we got really good initialization functions and some other tricks, the only way to train a deep neural network was to do it a layer at a time using restricted Boltzmann machines in this fashion.
You're essentially learning an identity function. I mean, it's similar to PCA because when you do matrix factorization in PCA, your principal component for telling you what percent of the variance you have of each component. So you're reducing your feature space. Here you're just basically, you're saying, is it possible to take 4 inputs, explain it by 2, and from those 2 get the 4 back, meaning that if my combinatorial power is high enough, the 2 in the middle are an adequate representation of the other 4. That's what you were saying. That
Yeah.
I think that's
Yeah, and actually you made a good point there, because when you have an autoencoder that's not deep, when you just have one single hidden layer, you're essentially just approximating PCA, because it's doing the same thing. So you're taking way longer and spending way more money to get to PCA. So when you're doing an autoencoder, ideally you do want to have multiple layers.
So I was gonna say, like, so say if you don't have like a lot of data, and like I say I run an autoencoder to make some fake data, and then you take the fake data to use to train back into the model.
Yeah, and actually that's really useful with like a variational autoencoder or some of these other types of autoencoders.
Yeah.
You can use them as generative models to
Yeah.
create new data, and there's
Right.
even other types of neural networks that can do that too.
Do you know anything on encoders do that as well?
Yeah, so it's a really interesting area of research. You'll see actually in the keras blog, and just from my own personal research that leads to stuff that I'm working on, I don't get a lot of success from autoencoders. There's a lot of other things that you can do, like we're going to get to in a second, like transfer learning, that tends to do a lot better. But this is a great introduction, and I think it's really important to understand this as a concept, because then you can start to do really, really creative things like the next thing I'm going to show you. So this is one of my favorite applications of neural networks, one of the coolest, kind of really simple but creative things that I've seen. And it's a little bit old, and I think other things work better than it now, but it's still just the idea that you can use something like this is really, really awesome. So what Skip-Gram is basically a methodology and an algorithm, and it's popularized by Word2Vec, which is something that Google created. And they basically created a neural network to learn from a whole bunch of text data. So it was like Google News or Wikipedia or something. They took all this massive, massive amounts of data, and they found where words were being used within the context of other words. So what ended up, I'll explain a little bit more, but final end of this model is actually, there was a model now able to project words into a coordinate space. So now you can actually see the proximity of words. Like the word king is close to the word queen. And you can do some really interesting mathematical operations where, like, king minus man equals queen and stuff like that, which is really, really cool. And so the basic concept of Word2Vec is based on the Skip-Gram algorithm. And so what it does is it just models the probability that the particular word that you have will be in proximity with all of the other words in your vocabulary. So you take all your text documents, you create basically one feature per word that now becomes your vocabulary. And now, with an autoencoder, what you would do is you would have your input word, and then the output layer would be that same word, and you're trying to reconstruct that word. But rather than that, what Skip-Gram does is now the final layer is the same size as your input layer because it is your entire vocabulary, but the output of each neuron in the output layer is the probability that your input word is close to whichever word that neuron corresponds to. So it's hard to read here, but you can see at the end the word that we have here is ants on the input. And then there's a bunch of hidden layers that's learning some sort of latent feature space. And then the output is the probability that ants will be close to the word abandon, or would be close to the word ability. And so what this does is basically learns this sort of contextual relationship between words, which is really, really exciting. And what this creates in this hidden layer right here is what's called a word vector, or an embedding. Again, it's a latent feature space. This is exactly what we're talking about, because what this network is trying to do is predict those probabilities of proximity. So now your hidden layer has some sort of intelligent, compressed, condensed space that's able to represent words in this like crazy mathematical way, which is really, really cool. And why I bring this up is because, again, like I said, autoencoders don't work well for a lot of things. This is basically an autoencoder, but tweaked a little bit on a different problem. And I think there's a really, really lot of capability you can do here. Yep.
How do you go from the previous slide of the autoencoder to making a generative model? So you're training, and how do you get from that to the next one?
So what you can do is once you have a set of training data, so data that you set aside to actually train your model, and then once you have new data, or you could actually re-feed back your training data into the model, because your hidden layer obviously is not going to be an exact copy of your input data. Even the output layer wouldn't be because there's some loss there in the reconstruction. But what you would do is be able to just run instances through that and then take the output and then save those as kind of quote-unquote new input data to kind of generate some new stuff. Exactly. And so you wouldn't do that with a regular autoencoder. You would do that with something like a denoising autoencoder because basically a denoising autoencoder, what it tries to do is it's assuming there's some sort of noise in the data, so it's trying to fix the noise. So it tweaks some of those, with an image, it tweaks some of the pixels to try to reduce noise in it. But in doing that, it actually creates a new instance because it's going to look different than your original one. So essentially, you're generating new data if you run it all the way through to the output layer. So
Your question was how to create a generative model with Autoencoder?
Yes.
Can you go back one slide?
yeah,
So this is a generative model from the latent space to the output. That's a classic generative model. After you train that embedded space, you start randomly creating vectors there, and you will see images.
yeah, it'll create
Whatever
some
you
sort of images. Yeah.
One more question. So, how do you go? I know autoencoders were part of it, but how do they make deepfake? Was that autoencoders changing the faces?
I'm not super familiar. Anybody else familiar with that?
That's generative design.
It's probably
Problem,
again
right?
because there's so much stuff around it. But if you're gonna make a generative model, you probably want like a variation autoencoder, which learns a distribution, because then you sample from that distribution, right? If you have an autoencoder that learns how to recreate things, it won't know how to recreate anything outside of the data set that it's seen.
Yeah.
That's the only thing it knows how to do. And so what you want is something that generalizes outside the data set. So in this particular case, learning a distribution or some multimodal distribution is a lot better for generative models than it is to just recreate the input, or learn a representation. They're two subtle different things.
Well, I think they are more close. The thing is that the big challenge with autoencoders, variation autoencoders try to deal with it, is that because of the loss function you use, you end up in mode collapse.
So that's for GANs. That's different.
No, autoencoders, they tend to collapse mode because you use mean square error. So you end up with something that is always fuzzy at the end. GAN,
Right. If you use that as your loss, the same thing was happening with GANs, and that's why we got things like the Wasserstein distance.
yeah, but you don't have labels in autoencoder. You cannot use.
You don't have labels necessarily with GANs either.
Yeah, but the discriminator helps. The last function you have with you use both functions, it helps with mode collapse, which that's why they perform better than. But essentially, they are very, very, very close related.
They are, the GAN and the variation encoder are definitely very closely related. I was talking about, yeah.
All right. So moving along. No, it's all good. So that was autoencoders, and then a little bit of little tweak and creative tweak on autoencoders. We're going to talk now about transfer learning, which is supervised neural networks, and then transferring that to a different place. It's again very similar concept. It's neural networks, same kind of architecture, but you're again mostly just changing your output layer and then what you're going to do with that. So the basic concept with this is a form of transfer learning. The term transfer learning kind of encompasses a lot of different things, but what we're specifically talking about is training basically a deep neural network on some sort of supervised learning problem with a lot of labels, where you actually do have labels on all your data. And it needs to be a large amount of data because you're trying to learn, again, a feature representation. So what you do is you train that whole model, make sure it can predict your original problem really, really well, but the same way with skip-gram, the same way with an autoencoder, is now you throw away your output layer. What you really care about is your last hidden layer that has your latent feature space. So what you do, you put in, essentially you're taking that pre-trained network and you're transferring it out to a different problem. It's going to have the same input dimensions, but now you're trying to predict something very different, sometimes very different. And I have a couple examples that can kind of solidify that a little bit more. So that's basically the main concept. It's very similar to the autoencoder, very similar to skip-gram, where you're basically training a model on something, but that particular thing that you're predicting is not really what you care about. It's whatever you're transferring that network to, and it's really the hidden layers that you care about. So a really, really cool example of this is a paper that came out from Stanford where what they did was they took the ImageNet data, which is a big data set of images that actually have labels. Like this image is a fire truck, this label is a dog, this image is a cat. And so they're training a state-of-the-art neural network model, and that's this big old thing right here. Is they took the architecture from the Google Inception v3 convolutional neural network that was pre-trained on ImageNet. So they were training it just on these regular images that are in ImageNet, just standard images that you would have of like a house or a car or whatever. And they took that pre-trained network, they transferred it now to a medical problem for diagnosing skin cancer from images.
Wait. What was the first part of the network trained on?
On ImageNet, which is just kind of basic images of just cars and dog animals.
They took I know what transfer learning did, but but they went from cars and dogs to melanoma.
Yeah.
It's a little bit subtle. It turns out the lower layers learn the basic features of mold.
Yeah, but still,
It makes sense. I mean, an edge is an edge.
It learned from images. It wasn't particularly that this image is something that's outside or that's a dog, but it just learned something that we as humans aren't going to be able to particularly get.
Oh, I understand it. I just didn't think you'd be able to make a jump like that.
I know, I wouldn't either, and I think it's crazy that worked, and it sort of worked. It's a little nuanced in the paper. Like they'll come out with press releases saying that we're better than dermatologists and we don't need them anymor. We're going to be able to diagnose all skin cancers.
Is there a paper for that particular?
Oh, absolutely, yeah. So if you look at the Esteva et al, yeah. So there's a couple there. It's on Nature. So there's like a Nature letter that's a shorter version, and I think there's an actual full length.
Is
Paper?
It, because Nature's paid for a subscription.
Yeah, I
just want to make sure that but not all of their content.
No, so this one is open access.
Okay, cool.
So the short letter, which is basically the gist of what they're doing, is an open access one. The deeper, longer one is something that you have to pay for. If you have a school account, you can get to it. But it's really interesting. Just again, it's showing what's possible. I put there in bold because I get paid from a company that's direct clients or doctors, and specifically dermatologists. But we're not replacing the dermatologist, right? If you think about somebody who can come into the doctor with like multiple skin lesions, the doctor may only have like 5 minutes to review all of those. So what you can do is if we have a model, obviously there's still some work that has to be done, but if you can have a model that you can take a photo of all these lesions and then the algorithm can say, okay, these 3 are the sketchiest ones that you need to look at. So now the doctor can really just focus on those 3 and then look at it, rather than just the machine automatically diagnosing in like a Prometheus kind of way.
Is transfer learning basically generalization? Taking things that you know here and seeing how they apply someplace else and basically learning.
Yeah, sort of, but
That's not
yeah, and it's limited generalization because it's not like you can then take this to like a text data set. There is some types of transfer learning which is called heterogeneous transfer learning, which means it's actually trying to use different types of input data. In this particular case, they had to actually scale these melanoma images to be the same exact size as the ImageNet images. So your input layer is exactly the same. So it's the only kind of thing that you're changing here is your output. So it generalizes a little bit, but not fully to where it's just like a magical model that's going to be able to predict anything. So
This may be a naive question, but when you transfer the existing training neural network and then you show it moles, right? Are you telling it giving it labeled data that says this mole is a melanoma, and therefore the output that it gives you is yes melanoma, and then you're giving it unlabeled data and trying to predict which ones are that? How do you convert the existing network to something tell you what the output is?
yeah, and so essentially you're going to retrain the network when you transfer it. So what the initial learning does is basically initializes your weights. So you can freeze some of those. Like if you have a really, really big network, you don't want to go and retrain the entire network because that's going to take forever. But you can freeze certain layers where it's like, okay, maybe the first couple layers I want to keep it as whatever ImageNet learned. But then it's all going to be labeled where you're now going to feed those, because a neural network you can just continually train forever, theoretically. And then you're going to pass in your new labeled data, and it's going to tweak some of those weights in some of the unfrozen layers, and then you're going to have a new model that has a different set of weights. So it's essentially, transfer learning is essentially just weight initialization. Yep.
This is like probably 18 months ago now. We had a meetup at your campus, I think.
FAU? Yeah.
Yes. And one of the professors, I don't know if he was a a neuroscience professor or something was mentioning how some of the deep layers in a model like this are very similar to ones we see in the brain doing something, I forget.
In the cat brain, and that is, we're not gonna.
Well, no, so the reasoning, I'll go back, 'cause it's not anything crazy. So he was mentioning, when we represent it like this, is very similar to this, and there's probably a reason. So could we go and edit those weights in middle layers somehow to make them exactly look like the representations we're getting from brains? I forget what he was doing, so it's kind of an important part.
Yeah, and like I said, and it is. It's I think it's a neuroscience or psychology professor. There's a lab there, which is interesting because it's not computer science, and they're doing a lot of really cool stuff. But it's loosely modeled on the brain. Like there's a lot more going on, and a lot more that we don't understand about the brain. But sort of, yeah. So I mean, like when you think about interpretability, you can kind of sort of trace where the input layer goes, and then which neurons and which layers it's firing, and then kind of what it creates as a kind of intermediate feature space. And so what our intuition is that some of these hidden layers learn like, okay, here's what an edge is, or here's what a curve is, or here's what the color red is. And so if you wanted to, you could go in and tweak that. It'd be really difficult to do so.
Yeah.
I
Yeah.
don't think it's possible to do it by hand because we don't really know the function that it's learning. So it's a black box as far as that's concerned. But if you want to know something really cool, is actually this year at NIPS, somebody grabbed biological representations from a brain and fed that into a clustering algorithm. And it turns out that our representations of information are extremely efficient, and they can give it to like k-nearest neighbor and do a really good job taking a representation created by your brain and using it to perform classification of objects. If you ping me on Slack, I'll send you a link to the video.
Yeah, so this is really cool, really awesome application of transfer learning. And then final slide before we dive into some of the code. We used, actually, this method was used when I showed you Eric Golinko's work on the gel algorithm. But what we're doing usually when we're learning a latent feature space is we're not just learning 2 features. You know, we're learning maybe 30 or 50 or 100. But to be able to visualize how well this is doing, like you can get metrics on that, okay, I'm predicting my class label 90% accurately. But a lot of times you want to be able to see it on a graph. You want to be able to visualize what kind of clusters it's creating. And so what an algorithm that you can use to do that is called t-SNE. It's basically just an algorithm that's really optimized for visualization. So you'll do a PCA, you'll run it through an autoencoder or something, you get now 50 features. You run those 50 features through the t-SNE algorithm, and what it does is it projects those 50 now onto 2 coordinates. So now a human can go plot this on an x and y axis, and you can label the dots based on what the class label should be, and then see the separation between those clusters. There's a lot of hyperparameters that you can tune again with t-SNE, and a lot of it is you kind of have to play with it. There's some rough ground rules for what you do with it, and if you want to look at that bottom right link from the Distill publication, which is a really awesome journal, check it out, even not just for this. Distill is really great. That explains kind of roughly how t-SNE works. You can play around with it with yourself and tweak some of the parameters. What I found, it comes out of the box in scikit-learn. You just run it until your graph looks nice, because that's really what this is about. It's not like you're going to be able deploying the algorithm into somewhere in production, but this is really just to be able to show how well your algorithm is learning the feature. So we're going to play with t-SNE a little bit too.
I just a question back on the transfer learning. Did they see, as far as like the sample size they needed for the melanoma prediction, did they just see a quality increase in the prediction, or did they have a large decrease in the sample size for the training?
So they used as much data as they could because it's hard to get the labeled data.
Sometimes data,
It is
those
limited.
volumes hard to
It is
calculate.
limited.
Yeah, I think they had on the order of tens of thousands, I think. But what they did is they had a doctor also. They had like 3 different doctors or something look at the image, make their predictions, and then they ran it through the model and compared it to that.
Yeah, but I mean, if they were just training basic from scratch by themselves, did they see a reduction in the samples? I don't, in what they would need to train the same model.
Right. I don't know.
Did they see like maybe from like tens of thousands to like thousands? Or...
I don't know if they did that in the paper, but that would be something interesting to check out. Just if you're doing this kind of thing, that's an interesting property to look at. Yeah.
The way my intuition behind transfer learning is that because you have a very deep model at different depth of the model, you get a hierarchical representation.
No, I understand how it works.
The first layers are very general.
Well, I understand. You do function composition and with identity functions.
So
The question was
it's like a way initialization.
I'm sorry, what's the question again?
No, I was just asking because sometimes when you're doing like image analysis, sometimes it's hard to come by tens of thousands of images for certain applications.
Transfer learning can learn with very little. The problem is the less data you have, the more regularization you have to do in order to avoid overfitting. Transfer learning gives you a lot out of the box. That's why if you're doing anything, you always want to start from a pre-trained model if possible. Of course, nowadays it really is because online you can find so many. Everybody has their models. Yeah, it significantly decreases the number of examples you need to answer your question.
Yes.
And you can do a pretty good job. As a matter of fact, and Metamine used to have a service where you can have a couple dozen images and it was pre-trained on ImageNet and you can do a pretty good job. Yeah, if you saw Eric Lamine's talk a few months ago on self-driving cars, he actually iterated over this as well. The biggest concern you have is overfitting and not being able to generalize. But there's lots of regularization and drama that you can use to early stopping to prevent your model from overfitting to those few examples.
No.
But significantly less.
Yeah, it's understanding that. It just like for instance, a lot of times if you train some of these models, you're working with like tens of thousands of images. It's one paper I was reading on disease detection with different types of crops and so forth. With a lot of pre-processing, they would do a decent job using in like around 10,000 images or so. But
Right, if you increase your signal to noise ratio.
yeah, you can do better. But it's like I was wondering like how, and I don't want to detract from the talk. I was just curious what in practice like. I was wondering what kind of savings they got by using the transfer learning as opposed to just training from scratch.
Pretty huge savings.
Like,
Pretty huge savings.
And I think that's one of the reasons, the only reasons it was even possible. I think
Yeah.
if they just changed it
Yeah.
straight from the medical images, it wouldn't have done nearly as well.
ImageNet has 25 million images.
Yeah, compared to they had like 70,000. I think. Don't quote me on that. But another question.
Yeah, just rotating the image, make it a different image.
Yes.
yes.
And so, if you want to introduce noise in certain ways like that, you can to kind of introduce, increase the size of your data, but it does create a different image.
There's a tutorial all on transfer learning on keras' website, which is super
Oh,
easy
cool.
to do. And you probably go through it in like an hour and a half. I did it for diamond classification, got really good results with a small.
For diamond
I'm not an idiot. So
Document.
it's super
Document.
easy.
Awesome. Yeah. Can you post that on the Slack? I'd love to read that.
Yeah.
Cool. Okay. So now the fun stuff. So we're gonna try to blow up some code. All right. So that was kind of the introduction to everything, and so we'll go through a couple of the methods now. It's in the GitHub that I posted. I'll put the link back up on the end of the talk. But really high level, just like I think we're going to do autoencoders, we're going to do PCA, and then we're going to do just a supervised model to show like the starting point of the transfer learning. We're not actually going to transfer it anywhere, but just to show how it works. So let me zoom in a little bit. So this notebook, you can just grab it. It's on the GitHub. It's fully rendered on the GitHub if you want to just look at it. If you want to grab it yourself, the data's on my S3, so it should just be ready to go to run. So what we're doing here is, again, I didn't want to use like one of the typical image data sets or one of the stuff that people are using neural networks and deep learning for everything. This particular case, just because it's something that I do, for my own research and in the space that I work in, this is going to be medical claims data. So we're taking data that Medicare publishes every year. They'll kind of create a curated data set which outlines for every single doctor, every single Medicare doctor in the country, all their medical claims, which is all the claims for procedures that they perform, the number of times they performed that particular claim, the number of money they requested, the number of money they made, the number of beneficiaries or patients that they had benefit from that claim. And so they'll release it every single year. They're usually a couple years behind. So like right now, the latest year we have is 2015, and they should have 2016 soon. So we got to keep an eye out for that. But we're going to take the 2015 data, and it's massive, right? There's millions of doctors in the country, and each of them do anywhere from like 10 to 30 procedures. So there's going to be tens of millions of instances in this particular data set. So what I did, you can see real quick in this notebook. I'm not going to run through it. I did a quick grep, just kick out Florida, grab Miami, just to get a smaller data set. So what we have here, I'll run this stuff so I can do things afterwards. So you can grab the data. It's pretty small. Don't download it too much because then I have to pay for it. It's on my S3. So I mean it's cheap, but just don't set up a bot or something.
I can have my company host it.
Oh, okay, cool. Yeah, I mean this is tiny. It's gonna be fractions of. It hasn't even come up on my bill yet. But yeah, if we get anything bigger, yeah, thank you. I appreciate that. So real quick, just so you can see what the data set looks like. Again, this NPI is just a unique identifier for every doctor. This is all public. You can go find a whole bunch of really cool data sets about like doctors getting payments from insurance companies and their education. You can see where their offices are and all that stuff. This is all publicly available from Medicare. So we get some names, everything. We don't care about that. What we're really going to look at mostly is this what's called HCPCS code, which is a healthcare procedure something. It's just a code that represents a procedure that's performed in a medical
Is there a
facility.
way for us to look that? I'm sorry, I didn't mean
Yeah.
to just ask. But is there a way for us to know what those codes mean? Is there somewhere we can?
Oh yeah, right next to it.
Oh.
But yeah, you can. What's funny is that just random information. This HCPCS code set is actually a superset of what's called CPT, which is the current procedural terminology, which is actually copyrighted by the American Medical Association. So it's hard to find a public data set that has the descriptions, but every single payer in the country uses it, Medicare being one of them. So you can kind of most of the time Google it, but technically it's copyrighted. The HCPCS superset, I guess, is not copyrighted somehow. But even in our application, we put copyrights on every page, saying that they want to make money, right? So that was a side note. Basically, this is all we care about. So we care about this code, which is the particular procedure. So this particular procedure was a physical therapy evaluation, and then what we're going to use in this case is line service count, meaning this doctor billed that particular procedure 217 times in 2015. This is the data types. We don't really care about that. So just some more data cleaning. I just grabbed anything that had the word Miami in it. Of course, there's a Miami, Ohio. There's Miami roads with the word Miami in it. So you can see that some of these cities aren't actually in Florida. So what we're going to do after that is we're going to make sure that the city contains the word Miami. And now these are all the cities we're looking at. It's trying to get to a smaller data set. Don't have to worry about that too much. Just some good data science practice, looking at our distributions of all of our fields, looking at what the data looks like. So at the end of the day here, we have 41,000 lines, 41,000 rows of data, and 26 columns. And that represents about 5,000 unique doctors that are billing Medicare in Miami. Some more exploratory analysis. We can see here, this is a box plot showing basically the number of unique procedures that each doctor performs. So the median doctor performs 5 unique procedures, but it can be from anywhere from 10 to 20. So we're looking about 5 to 20 procedures per doctor. So it's not crazy. But the thing is that there are thousands and thousands of unique procedures, but each doctor only does a certain set of them. So what we're trying to do here, this kind of toy example, is we're trying to take those procedures, all the procedures that a doctor does, and we're going to see if we can train a model that can figure out what type of doctor are you. Just based on the codes that you perform, can we predict your specialty? Now, some of these doctors, it's obviously going to be just natural intuition that if you're doing a bunch of skin biopsies, you're a dermatologist. If you're doing a bunch of radiology reviewing, you're a radiologist. So again, this is a toy example, but you can just to explain kind of what can be done. So we can see here the most frequent types of doctors is internal medicine, radiologist, cardiologist, and whatnot. So there are a lot of different types of doctors. So rather than trying to make like some 80 classification problem, we're just going to limit it down to like the top 10. So that gets a good amount of our data. We can 5,000 doctors are internal medicine, and then we can see this kind of tail drop off to see that. So what we're going to do is just take, I said 30 here, but that's wrong. We're taking the top 10. We're basically going to limit our data set down even further. So we're grabbing all doctors in Miami. We're grabbing only the top 10 most frequently seen, I guess, doctors. And we're going to clean this data set to do it for prediction. So what we're doing here, again, I'm flying through this. Like, you can go grab the code, ping me on Slack or whatever if you have some questions. But what we're doing is now we're just summing up that line service count, and we're getting a clean data set that says here's my doctor, here's their specialty, which is our class label, and then here's the HCPCS code. I combine the code in the description just so it's easy kind of to interpret, even though we're not actually going to interpret everything because we're doing feature learning. And then the line service count, which means the number of times they perform that procedure. So once we clean that out, now we have 4 features and 22,000 instances. But you notice in this data set, this doctor is still repeated. So what we want is we want one line, one instance per doctor because we're trying to predict that doctor's specialty. So since this data set represents basically, doctor code, doctor code, doctor code, we need to take those codes, flip them out, and turn those now into features. So what we're doing here is, we're doing a pivot, which is essentially what's called a one-hot encoding or dummy variables or whatever you want to call them. But this is a way to take categorical data, which is our codes, and then turn them into actually numerical features. And in this particular case, what we're doing is we're now creating a feature for every single code, and then the value of that feature is the line service count, the number of times that the doctor performed that procedure during 2015. So what this creates for us is a really, really sparse matrix because, like we saw, most doctors do anywhere from 5 to 20 procedures, but in reality, in our data set, we have actually 1,300 different unique procedures that are performed. So most of these doctors, like internal medicine doctor isn't going to be doing anesthesia for eye surgery, but somewhere in these 1,000 features, this particular doctor has anywhere from 5 to 20 of these filled in with a number. So this creates what's called a sparse matrix, meaning that most of the data is zeros for most of these entries, but we need to care about the ones where they're non-zero.
Are you catching any outliers for bad billing?
That's one application of this, absolutely, and that's part of why Medicare publishes this data because.
Somebody accidentally bills the wrong code and it gets paid or whatever, and it doesn't get fixed until maybe after that data gets released.
Yeah, absolutely. That's not something that I'm directly doing, but it's definitely one application of this data set. Fraud detection is a big one. So, it's a big problem, right? And part of why Medicare is publishing this data so people can kind of do this stuff and figure it out. And it's an interesting one, right? It's like if some internal medicine guy is doing all these like eye surgeries, it's like, well, maybe something's wrong here. So we've got a sparse matrix. I have a little rant on sparse matrices that we can pretty much ignore for now. You can look at that later. SciPy and Python has some really great tools for handling this stuff. You don't really have to think about it. You have to think about it a little bit, but not a whole lot. So again, just for the sake of time, we're going to breeze through it and show some of the cool, pretty graphs. So now to the actual feature learning. That's the introduction to our data set. We have doctors. We're trying to predict what kind of specialty they are based on the procedures they perform. So really, really easy. Like I said, scikit-learn just has all the stuff out of the box for you. So scikit-learn, if you don't know, is a Python package for machine learning. It's really the go-to for Python. So when you're doing feature learning, and especially with PCA and with neural networks, you want to scale your data. You want to make sure that all of your data has like a zero mean, that it's centered and everything. Because if you have one instance that's like age, that goes from anywhere from 0 to 100, with another one that's income, that may go anywhere from 0 to hundreds of thousands. You want to make sure that they have that you scale that data to make so that that way the model doesn't get like confused and it can get those correlations between data a little bit better. You can do it on raw data if you want to, but it works better if it's scaled. So really easy. If you want to do PCA, you just say PCA, and then you give it your data. So we're transforming the data into the scaled data, and we are now creating a PCA kind of representation. So here's how you can see where it's completely not interpretable now. Once you train a PCA on it, what PCA gives you back is basically all of those transformed data, and it actually gives you back the same number of features that you gave it. And so now the thing though is each one of these columns now represents your input data passed through one of those principal components. So principal component 1, 2, 3, and so on. So what you do with PCA is, again, your whole goal with this is to do dimensionality reduction. So you're going to take your input. We have 1,300 features. We want to reduce it down to somewhere like 30 or 20 or 50. So what we do is, because each particular principal component represents a certain amount of variation in the data, we want to see, well, how many of those principal components do I need to use to actually be able to be useful with this model? So the typical go-to thing to do here is what's called a scree plot. Basically, on the x-axis, each one of these points represents one of your principal components, and then the y-axis is now your cumulative proportion of explained variance. So now this is basically saying when you stack up all these principal components, how much of the variation in my input data am I getting to? And most of the time, you're going to see a nice, pretty kind of asymptotic graph here where you don't have to go to all 1,300 principal components because then you could just use your original input data. What you want to do is say, okay, where does this kind of start to level off? And in our particular case, we can go anywhere from 200 to 400 principal components, and it explains a significant proportion of our variance in the data. So from there, there's just a couple helper functions I have, just some Python magic to plot this stuff. So what we're doing here is I'm just plotting the first two principal components. So because, again, we want to be able, a human wants to be able to see this. So rather than take the first top 200 that explain most of the variance, I want to be able to show you that the first two components alone aren't good enough to separate and cluster our data, right? And so, like, you can see these colors are corresponding to all the different provider types, but the first two components alone aren't going to be enough to build a model on. But for visualization, that's why we brought in t-SNE, because what it does is it takes, again, it can take those top 200, top 50, or whatever, then creates a representation for you to be able to plot on a coordinate axis. So t-SNE happens here. Again, it's really simple. It's just call t-SNE, put in some of your parameters, and tweak them until it works. The one thing that's annoying about it is it's a lot of computation is happening, so it actually takes a long time. It actually took longer than the PCA took. It took 30 seconds just to be able to make the t-SNE. I don't think I put a time on the PCA, did I? No, I didn't. But we can see it. Watch. No, I can't. Never mind. But it's really, really fast. PCA is super fast. t-SNE takes a little bit longer. That took about 30 seconds. So, but now I took, let's see, what did I do? I took the top 50 features from the PCA, top 50 features, put through the top 50 principal components, and then I used t-SNE to transform that into two coordinates. And now you can see there's actually a good amount of separation in our data, which is basically saying that explained variance is actually explaining the variance that leads to the specialties that these doctors perform at. So I know it's hard to read, so I can point out a couple of clusters. So one of these here is ophthalmology. It's a nice little separate cluster here. Diagnostic radiology is the light green that's mostly separated. But some of the stuff that you see here kind of crossing clusters are kind of what you would naturally expect, right? The yellow dots are family practice, and the gray dots are internal medicine. So you can imagine those types of doctors are seeing all kinds of different patients. It's essentially, they're referring all these people to the other specialties, but they're going to be doing a lot of the same procedures. So naturally, the model would get confused because it's seeing similar procedures between those. So I thought this is really cool, and it's a nice, pretty graph. I'm definitely all about pretty graphs. So that's PCA. Again, I'm not gonna stop for questions just because we're running low on time. But talk to me after, ping me on Slack if you want to know more about the code. Next up is an autoencoder. So this is using our fun, friendly package. Keras is again, it's like a wrapper on top of TensorFlow, which is a mathematical library that's used a lot for machine learning, specifically neural networks. Keras makes it really easy to design, build, and test networks. So what we're doing here is I'm creating a model saying I have my input shape, which is about 1,300 features, and then I'm going to do a fully connected network with my first hidden layer is going to have 500 neurons. My second hidden layer is going to have 50 neurons, and that's my encoding. That's my latent feature space. And then I have to back up all the way to recreate now my input data again. So we can see here that our layers, the input shape is going to be exactly the same as the output shape because that's what an autoencoder does. And then this layer right in the middle is now going to be our latent embedded feature space. And you can see the total number of parameters here, basically the number of weights, is 1.4 million. So a lot of training that has to happen. Obviously, this is a toy data set, so you can actually run it on your machine and it won't take too long. I think running this through took 26 seconds, so you can see, track the loss as it goes down and whatnot. This is all just kind of boilerplate code. I didn't really intelligently choose the network architecture or the optimizer. This was, again, just for an example, just for everybody to get their feet wet. So what we do here is now you fit the model, and what's interesting is that with an autoencoder, you're fitting the same data that you pass in, right? You'd obviously want some splitting on the validation, but your input data, your X, essentially your independent variables, are going to be the same exact thing as your dependent variables. And now, once I have this trained model, after calling this fit method, now this deep _AE object is now my trained autoencoder, so with the encoding and the decoding. But I don't want that. That's not what I want. What I want is the encoded, the I care about is this layer. And that's part of why I named it. I put a name here to say this is the encoded layer. So we just do some internal care stuff to pull out what I want. So basically I'm now creating a new model, but it already has pre-trained weights. I'm taking my input layer from my initial model, and then I'm getting my encoded layer as now my new output layer. So what this does is it creates a new model, but it's already pre-trained. You're not training again, but now you can use it to basically predict or project some original data back through this network to create now 50 features. So rather than 1,300, now you get 50. And this is bad practice because I'm putting my training data right back through for testing. You don't want to do this in real life, but again, this is just a toy example. So because we want to visualize these top 50 features, we're going to run it through t-SNE again, and then we're going to plot it on this graph and see why autoencoders don't work for me, at least in this particular scenario. It was not able to learn any differences. I mean, at least it went on the graph and they're all spread out somewhere. Part of this could be that, again, the data set was really small. There wasn't enough for the network to learn. I didn't train a good enough network. I didn't train it for long enough. There's all kinds of reasons why this didn't happen. But, you know, kind of another testament to if you can just do PCA, just do PCA. It's fine. But I wanted to at least give everybody the code to run an autoencoder.
I think that's actually a good point to be made here, is that everybody talks about successes, and that's what we hear about. But you learn just as much or more from the times that you didn't get it to work than when you did get it to work. I think this is freaking awesome that you included it, and of course all the different issues that you brought up are relevant when training these things. But I think it's super important. I personally learn better from when my stuff doesn't work than when it works, because I tend to not think about it and let training go on to the next thing. This forces me to think about what's going on underneath the hood. But just a note, I think that's awesome.
Yeah, absolutely, and that's exactly how I got to this place. Was because I like, okay, I need to do neural networks in my research. I'm like, I'm hitting a wall. I need to do something. So I went through a few months and learned all this stuff, and then also didn't work. So I'm kind of having to go back, but now at least I got to talk out of it. So I guess that's one thing that worked. But it'll work eventually. I'm confident. I'm optimistic at least that something will work. So we're not going to quite do transfer learning, but I wanted to at least show like getting towards that particular place. So we're going to do a supervised training to basically predict those top 10 provider types, with the idea that now you can take the encoded hidden layer to go use it for some other sort of prediction problem. Maybe you want to predict how much money each doctor is making, or you want to predict something else, like where they live, or who knows. But same idea. It's very similar, again, to what you saw with the autoencoder, except the difference here is our output layer is now a different thing. Like our output layer now is has 11. Actually, it's actually the top 11 because I said, grab everything with an index up to 10, 0 indexes. So it's top 11 providers, but forgive me for that. So what we're doing here is the same input space. We're going to do a couple hidden layers. We're going down from 500 to 100 to 50. Again, we're going to treat this 50 as the encoded layer, even though we're not actually going to use it for something, but you theoretically could. And then now our output layer has 11 neurons, each of those neurons corresponding to each doctor, each specialty that we're trying to predict. And you can see that this actually has about half the number of parameters as your autoencoder, and that's actually another challenge that you have with autoencoders is when you create an autoencoder, that's basically double the size of any sort of supervised model that you would be creating, because you have to basically back to your input data. So you're adding a whole bunch of weights there, especially if it's fully connected. So that will significantly increase the time it takes to train your model. So this is a multi-layer perceptron because it's fully connected. Same idea, we're training it, except now this particular case, our loss is going to be the categorical cross entropy, and then we have metrics that we can use now because this is a supervised problem. We can actually see what the accuracy is. So we can see that the accuracy starts off 30%, which with 11 categories, it's not great, but it goes up a lot. And what we really should be looking at is our validation accuracy to make sure we're not overfitting. But at the end of the model, we get a 77% accuracy, which is decent, in a validation set, especially considering you have 11 classes. You're getting those 77% of the time is really good. A random guess would give you about 10%. So here's just some regular stuff, some supervised learning metrics we're going to get. We can see that 88%, 0.88 precision, recall. This is just typical metrics that you'll see in machine learning that I can't go into right now. And we can see a confusion matrix again to see, the confusion matrix shows basically the actual of your data versus what the model predicted. And we can see that the diagonal means that the model predicted properly, right? So the columns here, the rows here are the actual, and then the columns are predicted. We can see that we predicted, most of our anesthesiologists correctly. But what's interesting to note here is that family practice, we can see that we're confusing the family practice for internal medicine, or we're confusing internal medicine for family practice sometimes, and vice versa. So again, it shows what we saw in the PCA graph. And then again, if you wanted to get your new transformed feature space, you can do that. So now we take my encoded layer, we're grabbing those 50 features. Again, it's 50 features that the model learned. And we're throwing this through t-SNE again to see what we can do as far, what we can see as far as visualizing the cluster. So it looks similar to PCA. The clusters look a little bit different. I could have tweaked the t-SNE parameters to change them a little bit, but we're still getting confused here with family practice and internal medicine. So there's definitely more that can be done there. As a comparison, I wanted to show you PCA. Here's PCA. Going back, here's a neural network. So again, PCA works for a lot of things. So that's the thing, you need to try that first. If that doesn't work, now you can go to neural networks. It'll save you a lot of time and headache too. Much easier to do. So with that, we've got 8:45. That's pretty much it as far as code. So I'll go back to the slides and see if we got any more questions. Go to that website if you want a job. So.